Okay, so the last DP example we're going to look at is something called the house robber problem. This is comparatively very simple compared to the other examples we saw so far. So the problem statement is you have n houses, each has a specific value, so v1, v2 up to vn. Now there is a thief who wants to steal from these houses. So if he steals from a house, he acquires value equal to whatever value was assigned to that house. So if he steals from the second house, he gets value equal to v2. If he steals from the sixth house, he gets value equal to v6, and so on and so forth. Now he can rob from multiple houses, the only constraint being he cannot steal from any two houses which are adjacent to each other. So if he robs the ith house, he cannot rob from I minus 1 or I plus 1. So these are the constraints given to us. So with this, we are asked to find the maximum value he can steal given a bunch of houses with their respective values. So for example, if this array is given 19, 17, 21, 30, it means we have 4 houses. The values are 19, 17, 21 and 30 respectively. They are asking us what is the maximum amount he can steal subject to the non-adjacency constraint. If you look at the different possible combinations, you will see the maximum is 19 plus 30, which is 49 units. So obviously this is a maximization problem, which is optimization, and of course there is an interdependence, because if you steal from the ith house, you cannot steal I minus 1 or I plus 1. If you don't steal I, you can steal from I minus 1 or I plus 1. And the maximum value you can obtain from, say, I houses depends on the maximum you can get from I minus 1 houses, and so on. So there's a lot of interdependence between the problems, which means this qualifies as something which can be solved using dynamic programming, which is what we're going to see now. So again, we will go back to our basic principle of DP, which said the dimension of the DP table is usually equal to the number of input parameters we get. So here we have just one input, which is an array containing the values of the houses. So our DP table will also be just one dimensional table, or an array you can call it. And for each house you have a column. The base case is of course no house robbed, meaning the value is 0. Now DP of I represents the maximum value that can be obtained by robbing houses up to the ith house. This again is very important, as in any dynamic programming question, you have to understand how the value of each cell is defined. So here DP of I is the maximum amount that can be obtained by robbing any of the houses up to I. So it is not necessarily just I, and of course it cannot be all houses because there is this non-adjacency constraint, but some subset of the houses from 0, 1 to up to I, if they are robbed, what is the maximum value that can be obtained? That will be the value in DP of I. Now no house robbed of course is 0, which is straight up common sense, there is no explanation needed. For the first house, or rather let me say the 0th house, the maximum value obtained so far can be if you rob that house, it's the value of that house. If you don't rob, it's going to be a 0. So obviously the maximum will be when you rob that house, so it becomes value of that house. So DP of 0 is equal to value of 0. This is the initial table setup. Now for the rest of the houses, we have to come up with our optimal substructure as usual. So here if you look at this problem, you will see that it's, in a way, it is very similar to your coin change problem. So in the coin change problem, at every step you had two options: either you pick that coin or you don't pick it. Similarly, at every step in this problem you have two options: either you rob this house or you don't rob it. So if he chooses not to rob the ith house, then the maximum value he had after I minus 1 houses is going to remain the maximum value after the ith house as well, because he is not robbing anything new. So in that case, DP of I will be equal to DP of I minus 1. If he chooses to rob the ith house, then he is getting value equal to that of the ith house plus maximum value up to I minus 2th house, because if he is choosing to rob the ith house, it means he has not robbed from I minus 1th house. He cannot rob because there is a non-adjacency constraint. So whatever maximum value you obtained up to the house number I minus 2, that plus the value of this ith house. So it will be val of I plus DP of I minus 2. So for so these are the two options you have at every house, And since this is a maximization problem, obviously for every house you choose the greater of these two. So to summarize the optimal substructure for this problem, you can say dp of I equals val of I if I equals 0, meaning for the very first house or the 0th house, the maximum value that can be obtained is equal to the value of that house itself. It happens when you rob that house. For all the subsequent houses, it is max of dpi minus 1, comma, val I plus dpi minus 2. The former case dpi minus 1 being when you do not rob the ith house. The latter case val I plus dpi minus 2 being when you do rob the ith house. So that is the optimal substructure, and this is the same table we had. This is how we fill in the value. So this is very straightforward. This is your I value in each case. You have your formula here, you have the numbers here. So you just have to plug in the values, do the computation and fill in. And of course, as always, the last grid or the rightmost grid will be our solution, because the question says maximum value that can be obtained by robbing any of the entire 6 houses or 7 houses. So of course it will be dp of 6, which is the maximum value that can be obtained by robbing any number of houses between 0 to 6, and in this case it happens to be 19, which means for this particular instance of the house robber problem, the maximum he can obtain is 19 units.